This presentation is part of a lecture series on multi-resolution signal and geometry processing by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series, as well as the corresponding textbook, can be downloaded from the website whose URL is given on this slide, in particular this URL here. Having had a brief introduction to OpenGL and also having looked at the GLUT library, now we're ready to start looking at the OpenGL library in detail. The OpenGL library has many functions, but all of these functions have an identifier name that starts with GL in lowercase letters. And there's quite a number of different OpenGL commands, and each command has a number of different variants that differ in the number and types of the parameters that are required. And unfortunately, OpenGL not being a C++ library, it being a C library, there's no function overloading. So there's a lot of, for a single command in OpenGL, there's a lot of different variations on how you might invoke that command. In other words, there's a number of different ways you might specify the parameters and the types of parameters. Again, because we don't have function overloading, we have to give each one of these variants a different name. So OpenGL follows this naming convention for a lot of its functions, where the first part of the function name is some generic name, maybe vertex, for example, to say that this command is specifying the position of a vertex. Then we have a bunch of other letters or numbers that follow this that specify, like, how is the vertex specified? Is it specified as an xy coordinate, in other words with two coordinate values? Or is it specified with xyz? Or is it specified with xyzw, in other words a homogeneous coordinate, and so on. Also, we can specify the coordinate values as doubles or floats or ints. There's a number of different variations there. And then also we can specify a pointer to an array which holds these values as opposed to passing the values themselves. So there's a number of different variations on how things are named, but all of them start out with some generic name, and then this letter N here corresponds to the digit 2, 3, or 4, which is specifying how the coordinates associated with this particular command are specified, whether it's an xy coordinate or xyz or homogeneous coordinates. The next part of the name, T, is either one or two letters indicating the type of the components that are specified. For example, either they're bytes or shorts or ints or floats or unsigned bytes or unsigned shorts or unsigned ints or doubles. So these different combinations of letters indicate the type of the data that's associated with the generic command. And then V is the V here is corresponding to either nothing or the letter V in lowercase, which indicates whether or not the components are being passed in a vector, in other words a pointer to the array containing the data is passed, or whether the values themselves are passed. So for example, there's a command called glvertex3f, or a function called glvertex3f. This is a specific version of the glvertex function or glvertex command. In other words, it specifies a vertex position. And this particular variation, because there's a 3 here, it takes 3 parameters, and because of the f here, they're floats. So it takes the x, y, z positions as floats. glvertex3fv is another version of the glvertex command, but this one takes a pointer to 3 floats. So the components or the coordinates are specified in terms of an array. In OpenGL, the basic building block for all geometric primitives such as line segments, triangles, quadrilaterals, polygons, and so on is the vertex. A vertex just corresponds to a point in space, and a vertex is specified with the glvertex command. The reason why I write it as glvertex star, here the star can be replaced by various letter and number combinations that were discussed earlier. For example, glvertex2f or glvertex3f. These are all versions of the glvertex command, which I denote the generic command by putting glvertex star. So in principle, OpenGL works exclusively in terms of homogeneous coordinates. And internally it uses homogeneous coordinates. But for convenience, it allows you to specify coordinates in other ways, not using homogeneous form. So for example, you can specify a vertex with just 2 coordinates, giving the x and y coordinate, in which case the z coordinate will default to 0, and the homogeneous coordinate, the normalizing coordinate, will default to 1. Or you can specify 3 coordinates, in which case this will correspond to the homogeneous coordinate x, y, z, 1. Or, of course, you can specify all 4 homogeneous coordinates explicitly using GL vertex 4f. So, for example, the point in 3-dimensional space that has coordinates 1, 2, 0 could be specified using GL vertex 2f by specifying 1, 2, in which case the z coordinate defaults to 0, and then the homogeneous coordinate, which is not specified, will default to 1. Or we can specify the point using GL vertex 3f, in which case we explicitly specify the x, y, and z coordinate as 1, 2, and 0 respectively, and the homogeneous coordinate, which we don't specify, defaults to 1. Or we can explicitly specify all the homogeneous coordinates, as we're doing here with GL vertex 4f. So we say 2, 4, 0, 2. Since the normalizing coordinate is 2, this is equivalent to the point in space with the x coordinate 2 over 2, which is 1, the y coordinate 4 over 2, which is 2, and the z coordinate 0 over 2, which is 0. In OpenGL, all geometric primitives are specified by vertices, vertices simply being points in space. And to specify a vertex, the GL vertex command is used. In other words, the family of functions whose names start out as GL vertex. So GL vertex star again denotes a whole family of functions. In order to specify how these vertices are to be interpreted, in other words, are they individual points? In other words, we're drawing points. Or are they pairs of points which correspond to line segments? Or are they triples of points which correspond to vertices of triangles and so on? This is accomplished by using the functions GLBegin and GLEnd. And basically what GLBegin does is it takes a parameter which specifies how the subsequent vertices are to be interpreted. Are they individual points, pairs of points that represent the endpoints of line segments, and so on. And then GLEnd indicates when we're done specifying the vertices associated with the GLBegin function call. So for example, if we want to specify a bunch of individual points, we would call GLBegin and specify as a parameter GLPoints, where GLPoint says that all of the GL vertex commands that follow are specifying individual points in space. So we're going to be essentially drawing points. And then we terminate the drawing process with GLEnd, or the specification of vertices is ended with GLEnd. On the other hand, if we wanted to draw triangles, when we call GLBegin, we would specify the constant GLTriangles, which says that all of the GL vertex commands that follow GLBegin, they're specifying vertices of triangles. So there has to be some integer multiple of 3 calls to GL vertex commands that follow GLBegin, and each group of 3 consecutive vertices will be interpreted as vertices of a triangle. So for example, here this code snippet here would be essentially specifying a triangle whose coordinates are 0, 0, 0, 1, 0, 0, and 1, 1, 0 for its 3 vertices. And then we specify GLEnd to indicate that we're done specifying triangles. When the GLBegin function is invoked, there's a number of different types of geometric primitives that we can indicate that we're going to be specifying. And some of them we've already seen. We can specify the value GLPoints, which says that we're going to be specifying individual points in space. We can specify GLLines, which means that the vertex commands that we issue are going to always be issued in pairs, where a consecutive pair of vertices correspond to the endpoints of line segments. And then we can have a series of connected line segments, which is a line strip, or a series of line segments where the end of the last line segment is connected to the beginning of the first line segment. This is what we call a loop, line loop. We can specify GL triangles, which basically groups vertices into consecutive groups of 3, which are vertices interpreted as the vertices of a triangle. A triangle strip, which is a linked strip of triangles. A triangle fan is a linked fan of triangles. GL quads, if we want to interpret groups of 4 vertices as the vertices of a quadrilateral. Quad strip is a linked strip of quadrilaterals. And GL polygon for the boundary of a simple convex polygon. When we specify the vertex for a geometric primitive, the vertex has some other properties in addition to its position, which include color, a normal vector, texture coordinates, and material properties. If we want to specify a color for a vertex as an additional property, then before calling the GL vertex or invoking the GL vertex command to specify the position of the vertex, we first have to call GL color or issue the GL color command in order to set the current color. And then whatever color is currently in effect at the time when we call or invoke the GL vertex command, this is the color that will be assigned to that vertex. Similarly, we can specify a normal vector, in other words a surface normal, using the GL normal command. And no other call should be placed between GL begin and GL end other than either GL color or GL normal commands. So for example, if we wanted to draw a triangle but specify surface normals and also colors for the vertices, we would say GL begin, and we pass as a parameter GL triangles to say that we're going to be specifying groups of 3 vertices that correspond to triangles. So before we specify the first vertex, we call GL normal to set the current normal. So the current normal vector is set to 0, 0, 1 for its x, y, z components. So it's a vector pointing straight up in the positive z direction. Then we set the current color to be 1, 0, 0 in the RGB color space. So this is going to be bright red. And then after we've done this, we've set the current normal, we've set the current vector, then we call GL vertex to set the vertex position. And in this case, the vertex position will be 0, 0, 0. So this vertex will have associated with it whatever the current normal vector and current color is that's in effect. So it will have the color red and the normal 0, 0, 1, which we've set above here. Then we set the current color to be 0, 1, 0, which is bright green. And then we call GL vertex again. In this case, the normal will be the same as it was above, 0, 0, 1, because we haven't changed it. But we have changed the current color. So the current color for this vertex with x, y, z coordinates 1, 0, 0 is going to be the color we just set the current color to on the previous line, which is 0, 1, 0 in the RGB color space, which is bright green. Then after we've specified this vertex, then we change the current color again to 0, 0, 1 in the RGB color space, which is bright blue. And then we specify another vertex, which has the x, y, z coordinates 1, 1, 0. And this particular vertex is going to be associated with the color blue, because before we called GL vertex, we set the current color to blue on the previous line. And then, of course, we have to call GL end at the end to say that we're done specifying triangles. OpenGL has a very large amount of state. And by state, I mean, for example, various different options that can be turned on and turned off, and so on. And some of this state is controlled by the functions called GL enable and GL disable. And these are used for controlling state which correspond to options that can either be turned on or turned off. And there's quite a long list of them. I'll talk about some of them on the next slide. So as mentioned previously, the GL enable and GL disable functions can be used to turn on and off certain options within OpenGL. And what I'm going to discuss on this slide are a few of the options that can be turned on and off using GL enable and GL disable. So one of the parameters that can be passed, or values that can be passed to GL enable and GL disable, is GL call face. And what this is used to do is turn face culling on and off. And what face culling is, each polygon that you draw in OpenGL, so if you're drawing triangles or quadrilaterals, some kind of polygon, every polygon has 2 sides, the front side and the back side. And the basic idea behind face culling is, in some applications, you're only interested in the front side. You don't actually want to ever render the back side of a face. And in those applications, in order to save computation and not waste time doing computation related to the back side of faces, which you're never going to be viewing anyway, you can turn off the rendering of the backs of faces. And this is done by turning face culling on. So face culling basically disables the rendering of backs of faces. The next option we can turn on or off is GL depth test. This basically turns on and off depth buffering, or sometimes it's called Z buffering. And the basic idea behind Z buffering is that every time you draw a pixel with a certain XY value, the pixel value's Z value is also remembered. In other words, the position of that pixel or distance from that pixel from the camera or from the eye is also recorded, the Z value. And the next time you try to draw the same pixel location, it compares the Z value for the new pixel value you're trying to write to the old Z value that was written before. And if the new value you're trying to write is actually behind the value that you drew before, then no pixel value, the pixel value is not updated. So this gives you a very convenient way to do hidden object removal, a very efficient way to achieve this. So if you want to have depth buffering enabled, you need to make sure that it's enabled by turning this option on with GL enable. The next option we have is GL light I, where I is a digit like 0, 1, 2, 3, and so on. We can have a number of light sources in OpenGL. If, for example, we want to use light source 0 in the lighting calculations, then we would have to enable the option GL_light_0, which is the option to turn on the lighting or to use light source 0 in lighting calculations. To actually turn on lighting calculations, we have to enable the option GL lighting. So GL lighting actually turns lighting calculations on or off. The previous option we talked about only says that if lighting calculations happen to be turned on, then please use light source I in the lighting calculations. In other words, GL light I doesn't actually turn on or use the light source in the calculations. It doesn't turn on lighting. It just says that if lighting is enabled, please use this light source. So typically you need to enable both of these options if you want to do some kind of lighting calculations. Then we have GL line smooth. This just says that if you're drawing lines, they should be drawn with anti-aliasing so you don't get the jaggies, kind of an ugly aliasing effect that occurs in graphics. GL normalize is used to specify that the normals that you're providing with the GL normal command are not necessarily scaled to unit length, and therefore OpenGL has to do the scaling for you. So if GL normalize is enabled, OpenGL will automatically normalize all normals for you to be of unit length. Of course, it's more efficient not to turn it on and only normalize things when you really need to. But sometimes you may just want OpenGL to do all the normalization for you, in which case you can turn this option on. If this option is not on, and then you give OpenGL normals that are not unit length, OpenGL will be quite happy, it won't complain, but all the lighting calculations will be wrong. Everything will be out by probably some scale factor due to the fact that your vectors don't have the length that are expected by OpenGL. The next option, GL point smooth, just enables or disables anti-aliasing for the drawing of individual points. And then GL rescale normal, this option is related to the GL normalize option above. It enables the rescaling of normals inside OpenGL, but it only works depending on the particular transformation that you're using. It won't work in all cases, only for certain types of Modelview transformations and so on that you might have set. So GL normalize is a little bit safer. If you really know what you're doing and you know that the transformation you're using will work with GL rescale normal, then you can use this instead. Often when drawing points or line segments, we want to have control over either the size of the point that's drawn or the width of the line segment. And this can be controlled using the GL point size and GL line width functions. So if you're drawing points and you want to specify how big the point is in pixels, you can use GL point size to specify this. If you're drawing line segments, you can specify the line width in pixels by using GL line width. So you can essentially draw larger points or thicker lines. So for example, if we wanted to draw points that are maybe bigger than just a single pixel, for example 10 pixels in size, we can call GL point size 10, and then when we do GL begin and we specify GL points to draw a number of points, these points that we specify here with the GL vertex commands are going to be drawn with a point size of 10. On the other hand, if we're drawing, for example, some lines using GL lines, so we say GL begin, GL lines, and we give it pairs of vertices which correspond to endpoints of line segments, this is going to draw a single line segment with one end at 0, 0, 0 and another end at 1, 0, 0. But because we call GL line with 10 before we start specifying these vertices here, it's going to draw a line, like a thicker line, which has a width of 10 pixels. In a typical computer graphics system, a vertex undergoes a number of transformations as it passes through the graphics pipeline. The figure on this slide shows the various coordinate systems and transformations involved. So as you can see from the figure, there are several coordinate systems. We have object coordinates, in other words, the object coordinate system. We have world coordinates, which correspond to the world coordinate system. camera coordinates, which correspond to the camera coordinate system, something known as clip coordinates, which correspond to the clip coordinate system, normalized device coordinates, which correspond to the normalized device coordinate system, and then window coordinates, which correspond to the window coordinate system. And we also have a bunch of transformations that are used to map between these different coordinate systems. So the modeling transformation maps from the object coordinates to world coordinates. The viewing transformation maps from world coordinates to camera coordinates. The projection transformation maps from camera coordinates to clip coordinates. And then there's some clipping and perspective division process which will map from clip coordinates into what are called normalized device coordinates. And then finally, normalized device coordinates are mapped into window coordinates by what's called a viewport transformation. So what exactly are these different coordinate systems? So the world coordinate system corresponds to the coordinate system for the entire universe. So at the origin of this coordinate system is what you consider to be the center of your 3D universe that you're going to be rendering stuff from. Then we have the object coordinate system. This is the coordinate system that's used to define any particular object that you might want to draw. Then we have the camera coordinate system, which is the coordinate system relative to which the scene is viewed. So it basically indicates how the camera is positioned in space and oriented. And the window coordinate system is the coordinate system used to address pixels in the graphics window that you actually draw in the end. Now conceptually, it's helpful to separate the modeling and viewing transformations. We have this modeling transformation and this viewing transformation. Conceptually, they're separate things, and it's helpful for the purposes of understanding to think of them as two separate things. And sandwiched in the middle here we have these things called world coordinates. But in practice, often the modeling transformation and the viewing transformation are combined into a single big transformation. And the notion of world coordinates goes away. So basically this block here, modeling transformation, and this block here, viewing transformation, would be combined into a modeling and viewing transformation. And then there's no notion of world coordinates anymore. And in fact, this is what OpenGL does. There is no world coordinate system per se in OpenGL. On the previous slide, the projection transformation is the transformation that takes our three-dimensional world and flattens it down into a two-dimensional world that can be rendered on a two-dimensional screen. In practice, however, the projection, this flattening out process that's performed by a projection, is not actually carried out in practice, at least if you're using depth buffering, sometimes also called Z buffering. The basic idea with depth buffering is the graphics pipeline will keep track of the Z value, in other words, the depth or distance from the camera, all the way through until the very end where it's about to actually draw a pixel into your graphics window. And the basic idea is by keeping the Z information, it allows for a very simple technique to figure out whether or not there's something drawn in front of the pixel you're about to draw. Because if there's something already appearing in front of the pixel you're about to draw in your three-dimensional scene, you don't want to draw that pixel because it will block something that's actually in front of it, whereas instead the thing that's in front of it should block the pixel you're about to draw. So the basic idea is the depth information is carried all the way through. So in practice, projections aren't really performed per se. The Z information is carried all the way through. The projection really only happens at the last instant when the pixels are actually drawn. The figure on this slide shows the transformations that a vertex undergoes as it passes through the graphics pipeline in OpenGL. And in this pipeline, vertices are represented as a point in homogeneous coordinates. And there are essentially three key coordinate systems. There's the object coordinate system, the eye coordinate system, also sometimes called the camera coordinate system, and then the window coordinate system. The object coordinate system is the coordinate system used for specifying vertices of all geometric primitives in OpenGL. So when you're using GL vertex commands, you're specifying coordinates in terms of this coordinate system here, the object coordinate system. The eye coordinate system is the coordinate system relative to which the scene is viewed. It basically represents the coordinate system of your eye. And then the window coordinate system is the coordinate system used to address pixels in the graphics window. It's the actual coordinates used to draw on the frame buffer itself. Now, transformations are represented as 4x4 homogeneous coordinate transformation matrices. So the Modelview transformation, the projection transformation, and the viewport transformation are essentially homogeneous coordinate transformation matrices. although the viewport transformation in OpenGL, we never really directly view it as a matrix, at least not normally anyway. The Modelview transformation and the projection transformation appear to us very much visibly as 4x4 matrices. So when we draw things in OpenGL, we always specify the vertices in object coordinates. So we're basically specifying these coordinates that are represented by POBJ here, the object coordinates. Then as the vertex is passed through the graphics pipeline to do additional processing and eventually end up with the vertex being drawn in some way, the first thing we have to do is convert the object coordinates into I coordinates. So we have to convert into the coordinates represented by the variable pi. And we do this by a matrix multiplication, by multiplying by the model view matrix, which is denoted by m subscript m view. So if you have an object coordinates and we want to convert to I coordinates, we multiply by the model view matrix here. Similarly, if you want to convert to clip coordinates, which is the output of the projection transformation after we project things from a three-dimensional world into a two-dimensional world, converting from I coordinates to clip coordinates, this is done by multiplying by the projection transformation matrix, the matrix M subscript PROJ for projection. So if we have a point in I coordinates and we want to convert to clip coordinates, we multiply by the projection matrix. In OpenGL, the camera, or eye, is always positioned to be it's at the origin and positioned to be looking straight down the negative z-axis, with the up direction being the positive y-axis. There's no way to actually move the position of the eye. It's always fixed at this position. The coordinate system is always fixed in this way. However, this is not a big problem because although we can't really technically move the camera, what we can do is we can move the whole rest of the universe. And if you move the whole universe, you can simulate the effect of moving the camera. And in fact, there's a function called glueLookAt which simulates the effect of a different eye position and orientation. So by calling this function, you can essentially adjust the model view transformation so that it creates the illusion that you've moved the camera to have a different eye position and orientation, when really what you're doing is you're moving the whole rest of the universe by redefining what the object coordinate system is. But the end effect is the same. In OpenGL, two key transformations are the model view and projection transformations, as we've discussed. In order to be able to modify these transformation matrices, there's a number of functions that OpenGL provides, and these functions are listed on this slide. So I'll go through each of these functions in a little bit more detail. So the first function that can be used for updating the model view and projection transformation matrices is called GL matrix mode. And what this does is it sets the current matrix. The way OpenGL works is that all these other functions that are listed below, GL load identity, GLU perspective, and so on, all of these functions operate on the currently selected matrix. So you have a model view matrix in OpenGL and you have a projection matrix, and at any given time, one of these two matrices is selected as the current matrix. So GL matrix mode allows you to select which of these two matrices is considered to be the current matrix. Is it the model view matrix that is the current matrix, or the projection matrix? Once the current matrix has been selected, then you can perform operations on the current matrix, which is what the rest of these functions do. So GL load identity, what this does is it loads the current matrix with the identity matrix. And usually the pattern that you follow when you want to initialize one of these two matrices, either the model view matrix or the projection matrix at the start of your program, for example, is you'll select whichever matrix it is you want to modify with GL matrix mode, and then the very first thing you do is you load that matrix with the identity matrix. And then after it's loaded with the identity matrix, then you multiply that matrix by other matrices to set up the particular transformation that you want. The next function that's listed here, GLU perspective, what this does is it multiplies the current matrix by a perspective projection matrix. And this function takes a number of parameters which specify the parameters of the perspective projection. GLU ortho multiplies the current matrix by an orthographic projection matrix. GLU ortho 2D multiplies the current matrix by a 2D orthographic projection matrix. This would normally be used in the case where you're just doing two-dimensional graphics, so a more simple kind of graphics application. glueLookAt showed up a little bit earlier in this presentation. glueLookAt allows you to multiply the current matrix by a viewing transformation matrix that simulates the effect that the camera is positioned at a particular place in space with a particular orientation. So it simulates a transformation that has the effect of simulating the camera at a particular position and orientation. GL rotate F, it multiplies the current matrix by a rotation matrix, so in other words, it performs a rotation. GL scale F multiplies the current matrix by a scaling matrix, in other words, it performs a dilation. GL translate F multiplies the current matrix by a translation matrix, so it performs a translation. And then the two remaining functions, GL push matrix and GL pop matrix, they provide the functionality of a stack. And the reason for this is a very common sort of pattern to occur in OpenGL code, is you want to temporarily modify, usually it's the model view matrix. So for example, maybe you want to temporarily modify the model view matrix, do some drawing, and then when you're all done, then you want to put the model view matrix back to the value that it had originally before you changed its value. So a stack is a very convenient way to be able to temporarily save something and then restore it later. So the idea is, just before you modify the matrix, the current matrix that you're going to modify, you call GL push matrix, which saves a copy of the current matrix on a stack. Then you do whatever you want to do. You change the matrix however you like, do lots of drawing and stuff. And then when you're all done, then you call GL pop matrix, and that will read the old value that you pushed onto the stack. It will pop that value off and restore the current matrix to the value that was popped off of the stack. So we've discussed a number of functions that multiply the current matrix, either the model view matrix or the projection matrix, by another matrix. And these functions that multiply the current matrix by another matrix, they always do this multiplication by post-multiplying. In other words, the current matrix is always multiplied on the right by the matrix that's being multiplied by. This is important because matrix multiplication doesn't commute, so it makes a big difference whether you multiply a matrix on the left or on the right by another matrix. So I'll go through an example to help illustrate the process of setting up a model view matrix, in this case, by using GL matrix mode and some other function calls. So in this particular example, let's let the variable m denote the current model view matrix, and let p subscript obj and p subscript EYE denote the point in object and I coordinates respectively. So suppose that our goal is we want to set up a transformation that maps from object coordinates POBJ to I coordinates PI by first translating by the vector 1, 2, 3 and then rotating 45 degrees about the z-axis. This can be accomplished by the code that's shown here. So first we call GL matrix mode to specify that we want to change the model view matrix as opposed to the projection matrix, because in this example we want to use the model view matrix. So once we've called GL matrix mode, all of the subsequent matrix operations that we perform are going to be operating on the current matrix, which is now the model view matrix. So we call GL load identity first. This is going to load the identity matrix into the model view matrix, which we're denoting by m. So m will just be equal to the identity. Then suppose we call GL rotate f next. So this basically multiplies the current matrix on the right, in other words, post multiplies, by a rotation matrix, and the rotation matrix is a rotation of 45 degrees about the axis of rotation corresponding to the vector 0, 0, 1. So it's basically a vector which is parallel to the z-axis, pointing in the positive z direction. In other words, it corresponds to, using notation from earlier slides, it's a rotation 45 degrees about the z-axis. And we multiply the identity matrix on the right by this new matrix. In this case, it actually doesn't matter if we multiply on the right or the left because the identity is a diagonal matrix. But anyway, we do multiply on the right because in some cases it will make a difference. And this gives us the model view matrix is now this rotation matrix. Now next, suppose that we call GL translate to apply a translation. And we're going to translate by the vector which has xy coordinates 1, 2, 3. So we're going to translate by the vector 1, 2, 3. This is going to multiply the current model view matrix, which is RZ of 45. This rotation matrix here is the current matrix. It's going to multiply it on the right by the translation matrix T1, 2, 3. T1, 2, 3. So in other words, what this establishes is the relationship between object coordinates and I coordinates, which are given by this formula here. The thing that I've written here, RZ45, T123, this corresponds to the model view matrix. The important thing to note here is look at the order in which the transformations are being applied. In going from object coordinates to I coordinates, I first translate by 1, 2, 3, and then rotate by 45 degrees about the z-axis. So translation happens first, rotation happens second. The reason why this is important to point out, notice that the order of the function calls that you make, the rotation happens first, followed by translation second. In other words, the order that you apply function calls to modify the current matrix are backwards from the order in which the transformation appears in the equation here, the equation that relates the object coordinates to the I-coordinates. So be particularly careful about this. The order that you call the various different functions to modify a matrix are essentially backwards from the order that they're going to be applied to points. And this is a common source of problems for students. They sometimes will get the order of the transformations backwards. In OpenGL, if you have some window that you're drawing into, it's not necessary that you have to draw into the whole window. You can establish what's called a viewport. The viewport in OpenGL speak is the portion of the window in which you're drawing into. So you can make the viewport equal to the full size of the window, in which case all of the drawing that's done by OpenGL will use the full window. Or if you only want to draw into some sub-region within the window, you can set the viewport to be something smaller than the full window size, in which case the graphics will only appear in this smaller region within the window. And the viewport in OpenGL is specified by the function glViewport. On this slide, I've listed a few other functions in OpenGL that are particularly useful. The first of these is glClear. This is used to clear the buffer that's used for rendering. So you can, for example, clear the color information or clear the depth information and so on with this function. glClearColor is used to specify the color that's used to clear the color information when you clear the buffer that you're drawing into. glShadeModel is used to choose between flat and smooth shading. So smooth shading, for example, if you're drawing a polygon and maybe you specify different colors for the different vertices of the polygon, if you enable smooth shading, then OpenGL will interpolate the color information across the face so you get smooth transition from the color at one vertex to the color at another vertex. Flat shading is the opposite of this. There's no nice interpolation that will happen in that case. glFrontFace is used to define front-facing polygons. So for example, with the face culling option, you can turn on or turn off face culling, which will enable or disable the rendering of the backside of faces. The glLight function is used to set light source parameters, for example, the position of a light source, the color of the light that's associated with the light source. glLightModel is used to set lighting model parameters, for example, the ambient intensity of light. glColorMaterial is used to specify how material color should track the current color. So for example, when you specify a polygon, should the color information for a vertex be associated with both the back and front side of the face, or only the front, or only the back, and so on. This can be controlled with glColorMaterial. On this slide, I've listed a few good references on OpenGL. The first is a book. It's called the OpenGL Super Bible. It's quite a thick book and covers quite a lot of aspects of OpenGL. It even talks a little bit about the GLUT library as well. So it's a quite good reference on OpenGL. The next reference, the second one that's listed on the slide, is the actual specification, the OpenGL specification from the OpenGL consortium. The next reference is the OpenGL website. This is the official website from the OpenGL consortium. It has a lot of really, really useful information, lots of links to tutorials and so on, very valuable. And then this last URL that's listed here is the URL on the website, the OpenGL website, where the full documentation on every OpenGL function can be found. And this is very useful for looking up documentation on the various different functions.